All right, before we begin our lesson on improper integrals, I would like you to try a warm-up. So hit pause and come back and check your answer. All right, this one is pretty straightforward. There's nothing weird about this particular one. So we're going to take the antiderivative. We'd get the natural log of the absolute value of x plus 3 times the chain of x plus 3, which would just be 1, evaluated from 0 to 3. So we get the natural log of 6 minus the natural log of 3. And I'm going to not leave my answer this way. You probably will not see your answer this way. I'm going to use my log properties to get the natural log of 2. And this is the answer you will likely see on an AP multiple choice test. So hopefully that was pretty straightforward. And now we're going to dive into improper integrals. But before we begin improper integrals, let's talk about what a proper integral is. So everything we've looked at thus far are proper integrals. So the definition of a proper integral is an integral expression of the form, the integral from a to b of f of x dx. And it's considered a proper integral if the limits and the function are bounded. So what we mean by that is the function in the interval from a to b is defined, meaning it's not shooting off to infinity somewhere in the middle of that interval. And the limits of integration are finite. A and b are not positive or negative infinity. So really everything we've looked at so far has been a proper integral. But what happens when these conditions aren't that way, when they aren't met? Well, that is the definition of an improper integral. So there are actually two types of improper integrals that we're going to look at, and the definition says this. An integral expression of the form, the integral from a to b of f of x dx, it's considered improper if one of two things occur. Either the lower bound or the upper bound is infinity. So either a or b is infinity. Okay, so some examples that might be what that would look like. For example, if we had the, I'm not doing limits at the moment, the integral from 2 to infinity of f of x dx. Or if we had the integral from negative infinity to 5 of f of x dx. Or even if we have an integral from negative infinity to infinity of f of x dx. These would all be examples of the type 1 of improper integrals. So one or the other bound is infinity or negative infinity. Now, the other type of improper integral that we have is a region defined by f of x happens to have an asymptote, an infinite discontinuity, something where the graph heads towards infinity in the middle of the interval between a to b. So for example, an example you might see here might look like, I don't know, negative 1 to 1 of 1 over x dx. Okay, why? Why would this be considered improper? Well, we know that it has a vertical asymptote at 0, and therefore part of the graph is tending towards infinity at 0 as it approaches 0, and 0 is in the interval from negative 1 to 1, and so that makes it improper. So these are the two types of improper integrals that we're going to focus on. Now, we're going to start with the idea of the type 1, where one or the other or both of the bounds are infinity. So we're going to focus on that for a little bit first. Okay, so we're going to introduce some new vocab as well. There are actually 3 things that can happen, and don't stress about these different cases. You'll see what happens here, so don't worry about that. But let's introduce some vocab. The first thing that you need to know is that an improper integral is said to converge if the limit exists. And what I mean by exists in this situation is I mean it is a finite number. Otherwise, not infinity. And diverge, to diverge, we call an improper integral divergent if it does go to infinity at that point, or it does not exist at all. So to say it diverges means that the integral goes the value of the integral is infinity, or it just doesn't exist. All right, these two cases that were case 1 and case 2 that we're going to focus on today are actually going to be representative, let's do this, of these two right here. So case 1 and case 2 look like this. If my function's continuous on the interval from a to infinity, then we might have the integral a to infinity of f of x dx. Case 2 is if f is continuous on the interval from negative infinity to b, then we have an integral that goes from negative infinity to b of f of x dx. Now, in both of these situations, in order to deal with that infinity, is we are going to say that this is the limit as b approaches infinity. So instead of calling it infinity in my integral, which we don't know how to evaluate, we're going to take the limit as b approaches infinity. Meaning what's happening is I go from a to this other ending point. Or, similarly, I'm going to take the limit as a approaches negative infinity and rewrite it to look like a normal integral problem. That's case 1 and case 2. So in these problems, if I get that there is a limit as b approaches infinity or a approaches infinity, then I say that that integral is convergent, or it converges. Now, the third case is the improper integral actually has to have both integrals be convergent for the integral to be convergent, the full integral to be convergent. And if either of the two integrals is divergent, then so is the integral. Now, this is that third case. This is where the lower bound is negative infinity, the upper bound is positive infinity. Now, what we're going to do to set this up is set up two integrals. And what case 3 is saying is if both of these integrals are convergent, then this integral is convergent. But if one is divergent and one is convergent, then this diverges. All right. Now, when we set up these two integrals, we'll talk about it. We're going to go from negative infinity to some number c, and we're going to be strategic about how we pick that c. Now, that's the idea behind improper integrals. But to be honest, looking at these words doesn't really make it super helpful to be able to see how to solve this. So let's go through some examples, and hopefully that will help. Okay. There are some helpful hints that we're going to talk about when dealing with these improper integrals. The first, when you're dealing with improper integrals, you really have two problems that you're solving. Not one problem, we're solving two distinct problems. And the two problems that we're solving is an integral problem and a limit problem. And we're going to treat them a little bit differently, okay? Now, when we're breaking down the improper integrals, make sure that your integral is improper at only one place, meaning it's only improper at the lower limit or it's only improper at the upper limit of integration. If we have more places where this integral is improper, we're going to have to treat it a little bit differently. We're going to have to break it into more problems. All right, here we go. Let's look at an example. Let's look at the integral from 1 to infinity of 1 over x dx. The problem is this is improper because that upper bound is infinity. So what I'm going to do is I'm going to rewrite this as the limit as that upper bound b goes to infinity. It doesn't really matter what you call that upper bound. It could be b, it could be r, it could be s, it could be t. Doesn't really matter. I'm going to rewrite it as the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Now here's the deal. This is two problems. So the first problem I'm going to focus on is this integral right here. I'm going to do this. I'm going to use the fundamental theorem of calculus and I'm going to find this integral. So just rewriting the problem, I would have the limit as b approaches infinity of, and this integral here would be the natural log of the absolute value of x evaluated from 1 to b. And again, I'm still working on this integral problem. So I've got the limit as b approaches infinity of, this would be the natural log of the absolute value of b minus the natural log of 1. Okay, So let's talk about what we know. What do we know about the natural log of 1? Well, we know the natural log of 1 is really just 0. So really my problem now is the limit as b approaches infinity of the natural log of the absolute value of b. So let's talk about this. Do we know this limit? Do I know the limit as b approaches infinity of the natural log of b? Well, we've already looked at these. We know this is infinity. So what we can say about this particular improper integral is that it diverges. Well, now let's look at this integral again, only let's look at it in comparison with y equals 1 over x squared. So here we have the graph of y equals 1 over x, and that would be, it looks like it's this red line right here. So this is y equals 1 over x is the red line that we have right here. All right, now keep in mind, by taking the integral from 1 to infinity of 1 over x dx, what I'm actually doing is finding the area under the curve. So this area under the curve for x is greater than or equal to 1, and they didn't give an upper limit, really says that the integral from 1 to infinity of 1 over x dx diverges. We see that from above, so I'm not going to repeat the math on that. Now, let's focus on this y equals 1 over x squared. So that's the blue line. So we have this y equals 1 over x squared, and I'm trying to find the area under this curve when x is greater than or equal to 1. So setting up the problem, I would be doing the integral from 1 to infinity of 1 over x squared dx. Now, this is an improper integral, so I'm going to rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. And remember, I need to do two problems. I'm going to do the integral first and then take the limit. And what we have here is we have the limit as b approaches infinity of, well, taking the integral of this, I would get negative 1x to the negative 1, evaluated from 1 to b. So this is the integral. Doing that integral work, we would get the limit as b approaches infinity of, that would give me negative 1 over b minus negative 1 over 1. Okay, and that's the integral evaluated from 1 to b. And if I take the limit now, if I go and substitute in the limit now, what I know is that this integral right here, if I substitute in infinity, really just goes to 0. And so therefore, this limit, the value of this limit is actually positive 1, which means this function converges. Okay, so we hit pause and try the next examples, A, B, C, and D. Hint, A is one you need to do, D is one you need to do, B and C you've already done. And try those problems and see if you can determine whether they converge or diverge. So hit pause and then come back. All right, hopefully you had a chance to look at these. I'm going to go through the steps again for each of these. So we would take the limit here as b approaches infinity of 1 to b of x to the, I'm going to go ahead and write it as x to the negative 1/2. It just makes it easier to see when I go to take the antiderivative. So we have the limit as b approaches infinity of, the antiderivative of this would be 2x to the positive 1/2, because I'm going up a degree, evaluated from 1 to b. So I'm taking the limit as b approaches infinity, and using that fundamental theorem of calculus, we've got 2b to the 1/2 power minus 2 times 1 to the 1/2 power, so minus 2. And if I substitute in infinity here, whether you rewrite this using square roots or not, the limit here is infinity, and therefore this diverges. From above, we know this integral also diverges, and this one converges. What about this fourth one? What'd you get? So we've got the limit as b approaches infinity of the integral of 1 to b of 1 over x cubed dx. I'm going to rewrite that also as x to the negative 3. Now I am going to integrate, so we would get the limit as b approaches infinity. Go up a degree would be negative 2, divide by that degree. So this would be negative 1 over 2x squared, evaluated from 1 to b. So I'd be taking the limit as b approaches infinity of negative 1 over 2b squared plus 1 over 2, or minus negative 1 over 2, which would be plus 1 over 2. Now, the limit as b approaches infinity here, this one would go to 0. And then that leaves me with just 1/2. So therefore, this converges. Now, can I make a prediction about what I expect to be convergent or divergent? Meaning, if I look at the same type of problem, these are 4 of the exact same type of problems. Can I look at it and without going through this limit process every time, determine what converges or diverges? Hopefully what you noticed is the pattern is this integral from 1 to infinity of 1 over x to the p power, whatever p happens to be, is convergent when p is greater than 1, not equal to 1, because we saw up here with b that it diverges. And therefore, it's divergent when p is less than or equal to 1. So some examples of functions that actually converge on the integral from 1 to infinity would be 1 over x squared, 1 over x cubed, 1 over x to the 4th. Those would all be examples of functions that converge. Now, there are a few other examples of things that converge, so let's look at a couple others. If you're feeling adventurous, go ahead and try these on your own. So hit pause and then come back. If not, stick with me and we'll go through this together. All right, notice this one, the lower bound of integration happens to be negative infinity. So I need to treat this one just a little bit differently. Really the same problem, but we are going to replace that negative infinity, and that's the lower bound. So I'm going to say the limit as a approaches negative infinity of a is my lower bound, 0 is my upper bound, x e to the x dx. So this is 2 problems. First thing I'm going to deal with is the integral. So I'm going to deal with this integral right here. Now, I'm going to give you one hint that's a little bit weird about this particular problem, and that is that a approaches negative infinity. We can certainly plug in negative infinity. Another way that we can deal with this, if we don't want to deal with a approaching negative infinity, if it's easier for us to think in terms of infinity, one of the things that we can do is we can rewrite this problem. Rather than being the limit as a approaches negative infinity, we can rewrite it as the limit as a approaches positive infinity. But then this will be the negative a in the denominator, or sorry, not denominator, the lower bound to 0. So this is another way that we can look at the same problem. Now, there are pros and cons to both. Most of the time when you watch somebody work through these problems, they'll switch that lower bound to be negative, but not always. So feel free to do it anyway. Now, we need to figure out how to integrate this. Does it look familiar? Hopefully you think integration by parts. So this does happen to be an integration by parts problem. So I'm going to let u equal x and dv equal e to the x dx. And the derivative of u is dx, and the antiderivative of dv is e to the x. So now, using integration by parts, u v minus the integral of v du. Integrating that, we get x e to the x minus e to the x would have a plus c, but I'm going to plug this back into this particular problem, which has bounds. So this would be the limit as a approaches infinity of, replacing this with the integral, we'd get x e to the x minus e to the x, all evaluated from negative a to 0. Okay, so this would be the limit as as a approaches infinity of, using my fundamental theorem, we would get 0 e to the 0, so that would just be 0, minus e to the 0, which is 1, minus, now let's plug in negative a. We'd have negative a e to the negative a minus minus e to the negative a. Sorry, forgot what I was plugging in there for a second. Okay, keep going. We can simplify it from here just a little bit, so we'd get the limit as a approaches infinity, and this would give us negative 1 in that first parenthesis minus, or positive in this case, it would end up being a over e to the a plus 1 over e to the a, rewriting those all as positive. Now, this gives us a chance to practice our relative growth. I'm trying to find the limit as a approaches infinity. Okay, I know in this first function I have a polynomial and I have an exponential. Which is bigger? Which is growing faster? We know an exponential grows faster. So since the exponential is in the denominator, the limit as a approaches infinity is just 0. So this limit is 0. And same thing on 1 over e to the a. The limit as a approaches infinity there. I also have a polynomial over an exponential is also 0. So the result of this problem is actually just negative 1. And if I'm trying to determine whether it converges or diverges, since I got a finite value, we know this converges. So we get to use all sorts of fun techniques in this problem. All right, if you're feeling brave again, go ahead and hit pause and try the next example. All right, here we go. This one's different. This one's different because we have a lower bound and an upper bound of negative infinity and positive infinity. And we said that we need to pick a place where we can break this into two integrals. And I said we want to choose that c value, that one point that we actually know, pretty strategically. And the way we want to think about picking it is going to be based on the type of function we have. One, I don't want to pick a point that's going to be an asymptote in any form. Don't have to worry about it with this problem. Two, I want to pick a point at a bound of integration that's going to make substitutions easy enough. So in this particular problem, for example, I might rewrite this to be negative infinity to 0 of 1 over 1 plus x squared. And then I would add that to the integral from 0 to positive infinity of 1 over 1 plus x squared. All right, so now I have two problems. One has a lower bound that's a problem. One has an upper bound that's a problem. So I'm going to go ahead and rewrite these. That first one is going to be the limit. Lower bound is a. And I'm going to do a approaches infinity and just call this negative a. 1 over 1 plus x squared dx. Plus, then we have the limit as b approaches infinity of the integral from 0 to b of 1 over 1 plus x squared dx. Okay, now I have two problems. I've got the integral I've got to deal with first. So let's focus on each of these integrals. Now, hopefully you recognize that. We haven't had it come up for a little bit, but that is the arctan formula. So this first one would be the arctan that needs to be evaluated from negative a to 0. And the second one would be the arctan, I lost the variable, arctan of x. This would be the arctan of x that needs to be evaluated from 0 to b. And both of these still have the limits. So the limit as a approaches infinity and the limit as b approaches infinity. All right, now I'm going to evaluate using the fundamental theorem. So we've got the limit as a approaches infinity of the arctan of 0 minus the arctan of negative a plus the limit as b approaches infinity of the arctan of b minus the arctan of 0. Okay. What do I know about these? Well, arctangent means the angle that gives us a tangent of that number. So I can tell that the arctan of 0, the angle that gives us a tangent of 0 is 0. So those can go away. So then really this problem is the limit as a approaches infinity of the negative arctan of negative a. And then this next one is the limit as b approaches infinity of the arctan of b. Okay, this is going to require a little bit of thought. So if I substitute in infinity, what we're saying is where is it that the tangent approaches infinity? Can you picture your tangent graph? Can you picture the graph of the tangent that goes from negative pi over 2 to positive pi over 2? Right? And this graph, this tangent graph, looks something like this. So where is it that the tangent approaches, or where is it that the tangent's angle approaches infinity? Well, looking at my graph, I know the answer to this is pi over 2. This one is pi over 2. And therefore, the sum of those two is pi. And this converges. So that's the start of our improper integrals.